Hey class, so this is about where we left off last time in 3.5. So I can't remember if we hit this last time, but row operations don't change the row space, but they do change the column space. So even though numbers will change in the row when you do row operations, the rows, the span of those rows, they still will span the exact same plane or hyperplane or line or whatever they span. That's not true with the columns. When you do row operations with the columns, the column space does change. So this is a simple example. Then here we have 1, 1, and 1, 1. You do a row operation to get 1, 1, 0, 0. And the row space in both is just the span of 1, 1, right? The span of 0, 0 and 1, 1, that's still just the span of 1, 1. But the column space is the span of 1, 1, but that's different than the span of 1, 0. So that's what they're emphasizing here. Okay, this is the span of 1, 1 is the line y equals x, and the span of 1, 0 is the x-axis. So those are not the same. So those are going to be different spans. So this will be important when we try to find when we're trying to describe the column space. We might do row operations to find out where the pivot columns are, but we have to go back to the original matrix to describe the column space. The null space of a matrix, I was able to get to this in one of the classes, but not the other. Let A be an m by n matrix. The null space of A, denoted null of A, so it's a lot like row of A and column of A, is the set of all solutions of the homogeneous equation AX equals 0. So in set notation, it's the set of all x in Rn, so these are vectors, that you can multiply by a matrix A and get 0. So the null of A. So that A is the same as this one. We call it a null space, so it might not be too surprising to you that it is a subspace of Rn. The null space of an m by n matrix A is a subspace of Rn. In other words, the set of all solutions to a system Ax equals 0 of m of m homogeneous linear equations in n unknowns is a subspace of Rn. So we could start putting all of these in a set, any one that we found. If it's a square matrix and all the columns or rows are linearly independent, then the only thing in the set is the 0 vector, because A times the 0 vector is the 0 vector. But if we start having free variables, then we're going to have more. In fact, every free variable will add a dimension to the space that this spans. So here's the proof. So let's check and see if they fit the 3 subspace criteria. So V is in the null of A. This is just from the definition. The vector is in the null of A if A times V is 0. So is the 0 there? Yeah, because if V equals 0, then A times 0 is 0. So 0 is in the null of A. So let's pick two vectors in the null of A. So we do know that this is true, okay? But from the definition, this is by definition of the null of A. Then it is A times, so we have to figure out if this is in the null of A. Well, it's in the null of A if you can multiply A times that and get 0. So then we just do a little matrix algebra, you distribute. You know that each of these products is 0, sum is 0, so that's in the null of A. Similarly, you have to pick a U that's in the null of A and multiply it by some C, and we do the same go back to the definition here, what it means to be in the null of A, and multiply by A, and we have to show that that's 0, and you do your algebra, and you get to 0. So C times any U, any constant times a vector in the null of A is still in the null of A, so it's a subspace. So this is one of the most important things to understand about a subspace, is that we're going to be able to describe the subspace with a set of vectors, but we want the smallest set of vectors that we can get, but still span all of the subspace. And that smallest set, that smallest set of vectors that still spans is called a basis. So a basis for a subspace S of Rn is a set of vectors that they have to be linearly independent. Okay, so we don't have anything redundant, and it spans all of S. So the span of all those vectors, all the linear combinations, using some linear combination, we get to any vector in S. So it's, I like what it says down here. So the set is big enough to span all of S, but not so big that it becomes linearly dependent, so we don't have any extra or redundant vectors. So you can also think of a basis as being a linearly independent set of vectors in S that is as big as possible. So if you have a linearly independent set in S, but it doesn't span all of S, then you can actually find another one to add into the set, that will still be linearly independent. But it's also a set of vectors that spans S and is as small as possible. So, okay. These vectors, we have 1 and then all zeros, 0, 1, and then all zeros, down to 0, 1. Like these subscripts mean there's a 1 in E1 means there's a 1 in the first one, E2 means there's a 1 in the second one, En means there's a 1 in the nth one. This is called the standard basis for Rn. This corresponds to, like we have the x direction vector, the y direction vector, the z direction vector, the x, y, z, w if we had 4 dimensions. Like that's what these are. And they're called the standard basis. Those are ones we've been working with already in our, like when we think of the point 3, 2, we can think about that as 3 times 1, 0 plus 2 times 0, 1. So we've already been working with this basis. So this is called the standard basis. Really nice. Not always the best, but it is really nice. So here's another example of a basis. Oh, and if you have n of these in Rn, then it is a basis. So if we have 2 of these for R squared, then that is a basis with the 1, 0 and the 0, 1 vector. That's enough. We can span all of that. Any coordinate you give me in this plane, I can get there with just those 2 vectors. So that's one example. Another example, the columns of an invertible n by n matrix are both linearly independent, because if it's invertible, they're linearly independent, and they span Rn. So we get that by the invertible matrix theorem. Therefore, they form a basis for Rn. So if you have a 4 by 4 matrix, you know it's invertible, then you know the columns form a basis for Rn. The rows would also form a basis for Rn. Here's a set that forms a basis for R2. Let's see if this is 1, 1, 1, 1. Then we're over 1, down 1. And we are over 1, up 2. So those 2, they're linearly independent, and there's 2 of them, so they'll span 2 dimensions, so they are a basis. Find a basis for the planar subspace of R3 defined by the equation that? Well, it's a planar subspace, so we think, well, we'll probably need 2. And we do. It has dimension 2, although we haven't technically defined a dimension yet. From our experience, it seems like we'll need 2. As long as we pick 2 linearly independent vectors that are in this plane, then that's all we need. So I could pick one. I could pick any x, y, and z to make that true. So if I just pick, looks like 1, 1, 1 will work. So 1, 1, 1. So because 1 plus 2, 1 minus 3, 1 equals 0. Okay. So I need to find another one. What if I do 6, 6, 0, 2? So then I'd get a 6. My y's would be 0. So I'd get a negative 3 times 2. That would be a negative 6. So that would be another one. And these are linearly independent because there's only 2 of them. I can easily check one isn't a scalar multiple of the other one. So these would form a basis. So that's one way to do that. It might be a little harder if there's if we had to pick a third one for a third dimensional space. We could randomly pick 3, but then we'd have to check and make sure that by doing some row reduction to make sure they were linearly independent. Another way to do this problem is we know the vector 1, 2, 3, 1, 2, and a negative 3 is normal to that plane. The coefficients 1, 2, and a minus 3, that creates a vector that's normal. So we could pick anything, any vector that's normal. Any 2 vectors. We'll pick a vector u where that dot product is 0. Pick another one. Dot v where that dot product is 0. And as long as u and v are linearly independent, then we would be good. So, okay. So you can use the dot products here to find them also, and to define the basis. So as long as it's true and u and v are linearly independent, then u and v are a basis. Okay, I already did some work here to make so the video wasn't so long. Find a basis for the row space of A. So, yeah, row operations don't change the row space, but I do need to know if those rows are linearly independent. Because if they are linearly dependent, then the basis isn't all 3 of them. Then I would need to have fewer. So I started to do row operations, and you can see that once I did the first couple to get this first row, this first column well, then I had 2 rows that were scalar multiples of each other, but keep going, get a row of zeros. So already I can tell that I only need 2 rows. So I could just take the first 2 rows up here, and that would be good. That would be a basis. That's my basis number 1 right here. A basis isn't unique. There's lots of different bases. I could choose to take this column and this column, and that's my basis number 2. So, sorry, I said column, I meant row. So those rows, I know those are linearly independent, and they will span that same thing. I don't have to use that second one. I could have chosen to do the row operations differently. I do know that first row and the first one and the third one, the first row and the third row, they're also linearly independent. So I could pick the first and the third. And so that's my basis number 3. Any of these would work as a basis. I also row reduced it as far as I could, and I could write those as my basis So this row, those first two rows here. So that was my basis number 4. But any of those would form a row space. Really, as soon as I got to this first one and saw that I'm going to end up with the row of zeros, that I'd know, oh, I just have to take the first two, whether in the original A or in that first, or in this one here. Okay, so here's the theorem that connects spanning with bases. So if you have v vectors in Rn, then the set that's, if you take the span of all those vectors, we'll call that S, if all of those vectors are linearly dependent, then at least one of the vectors is a linear combination of the other vectors, and you can remove it. You can take it out. Notice they drop. There's a vk minus 1 and a vk plus 1, so they just randomly say, let's say it's vk that's a linear combination, so you can drop it, and the spans are the same. Like, we didn't need that 1, so removing vk doesn't change the span. And as long as S isn't just the 0 vector, then some subset of all of those is a basis for S. And the next slide, we're going to talk about how you'd need n of those, to need exactly n of those, and linearly independent. So the idea is to find a basis, start with a spanning set, and then throw away redundant vectors. So find a basis for the column space of B. Now here we have to be careful because row operations do change the column space. They don't change the row space, but they do change the column space. But luckily they've already given us a matrix that's row reduced, so we can see that we have three pivot columns here. Okay, so we can just take those 3 pivot columns. So the span of all the columns, it will span the column space, but we don't need all of those. That's not a basis, because we have a couple free variables. C2, for example, is a linear combination of C1. If I take 4 times this first column, I get the next column. C4 is a linear combination of C1 and C2. So if I take, that's a mistake, that should be C3. C4 is a combination of C1 and C3, right? 2 of C1 minus 1 of C3, that gets us C4. So we can throw away, we don't need this one. Okay, those would correspond with free variables in a system of equations. So our spanning set is just the remaining columns. So we just need C1, C3, and C5. There we go. The pivot columns of a matrix form a basis for the column space of A. So find a basis for column space of A, where A is row equivalent to the matrix B from the previous slide. Well, that's a really nice hint. We know that we can't take all of these because these are only 4-dimensional vectors, and we have 5 of them. So we know that we don't need all 5. Even without that hint, we know we need at most 4. But if we row reduced, we'd find that the first, the third, and the fifth one are pivot columns. Okay, because it said it's row equivalent to the matrix above, so we already know those are pivot columns. And so the column space of A, a basis for the column space of A, well, the column space will be the span of 1, 3, 2, 5, 0, 1, 1, 2, a minus 1, 5, 2, 8. Okay, and since these are all linearly independent, then this is also a basis. Okay, we had 3 pivot columns. We're spanning 3 dimensions. We need to have exactly 3 linearly independent. We need to have 3 vectors for our basis. They all need to be linearly independent, so that'll work. So even though this row reduces, and so that once you row reduce it, you could it's that we'd have 1 0 0 0 0 1 0 0 0 0 1 0 0. Too many zeros there. Even though this reduces and the pivot columns become this, this is not the same basis. This isn't the basis for the same column space as this is. They're not the same. Okay. One way to see that is here I have no way to get anything but 0 in that fourth variable. But here I have values 5, 2, and 8, so I can get different values in that one. So find a basis for the null space of A. Okay, so we've done a row space example, we've done a column space example. How about the null space? So you remember the null space is all vectors such that AX equals the 0 vector. So what we're going to do is augment it with 0 and find out, and we're going to augment it with 0, and then we're going to row reduce it. And I already, well, it already told us that it's row equivalent to the matrix B from the previous slide, and if you go back 2 slides, then it already gives us our complete row reduced form, so it saves us a bunch of work. So we need to figure out what all of the solutions are for this system. And we can see we have 2 free variables here. So I did what we do with free variables to describe the solution set. The solution set of this is the null space. So we've already done this. We didn't call it the null space. We just said describe the solution set. But you do the same thing. We rewrite it out as a system. You let your free variables equal itself. And then here I wrote all of the variables in terms of x2 and x4. And so I was able to write the whole solution as some number times this vector plus some number times that vector. And so the basis for the null space are linear combinations of these 2 vectors. So that's what I put right there. So the null space is the span of those 2 vectors. So any linear combination of those. So the way to find a basis for the null space is to augment it with 0, row reduce it. In this case, they'd already row reduced it. And then describe the solutions to that with any free variables. If there are no free variables, then the solution is just the 0 vector. But for any free variables, if you have free variables, then continue what we did in chapter 2 to write out the system in terms of in a vector form, and then the basis is the span of all of those vectors. So those free variable vectors. So in summary, row reduce A. If you're looking for the row space of A, row reduce A and take the non-zero rows. Basis for the null space, that's just what we did. Find the solutions to AX equals 0 and express them in vector form. Basis for the row of A. I think that's supposed to say column of A. Yeah, you take the pivot columns of A, but you have to row reduce to find the pivot columns. But once you find the pivot columns, you have to go back to the original A. Go back to the original columns of A, and those are the basis for the column of A. Just a few quick theorems to connect everything that we've been talking about. If S is a subspace with Bn and this set is a basis of S with n vectors, then any set with more than n vectors is linearly dependent. If it spans all of S, then if you add anything else in there, then you're going to create a linearly dependent set. the basis theorem, if S is a subspace and n is a basis of S with n elements, then every basis for S has exactly n elements. Okay, you need an independent, you need a vector for every dimension. So, and a linearly independent vector, a vector that's linearly independent of all the others for every dimension. And the dimension of a subspace, if S is a subspace of Rn, then the number of vectors in any basis for S is called the dimension of S. We've kind of already been talking about it that way, like a dimension of a span. If we span a plane that has, to describe that plane, you just need two linearly independent vectors. So the dimension would be 2, because that's the number you'd need in a basis for that subspace. Okay. So the standard basis has n vectors, and hence the dimension Rn is n. So a line L in R2 with a vector form x equals td has a basis d. So this, all the linear combinations of that vector right there, and that's the only vector you need. So the dimension of, and that's the basis for it. So you need it, but you can't, and you don't need any more. So the dimension of L is 1. A plane P in R3 with a vector form equation where you have linear combinations of u and v, it has a basis of u and v, hence the dimension of P is 2. So this is a tricky area that the book raises, is these might be three-dimensional. You might need 3 coordinates in there. They might be 3, 0, 1 and 1, 1, 2. And so you're like, is this a 3-dimensional space, or is it a 2-dimensional space? Like, what do you call it? Because there are coordinates in three dimensions. The coordinates are in 3 dimensions, but you only have a plane. So do you call it a 3-dimension or a 2-dimension? Well, once you have this idea of a basis, then it's easy to know. You have a nice way to define a dimension. That is, the dimension is the number of vectors in the basis. Find the dimension of the subspace here. Well, this is kind of hard for me to look at. So what I did was I rewrote it as a matrix where this is my A's and my B's and my C's and my D's. And then I couldn't clearly see, well, I could see that B and C are linearly dependent, but I'm not sure if the other ones were. So I started to row reduce, and I did get 3 pivot columns. So the dimension of this would be 3, because I have 3 pivot columns. So that these pivot columns, the original pivot columns, would form a basis, or I can look at the row. These are all, that row space with those 3 would span the space, and I only need 3 as a basis, so the dimension is 3. Okay. The dimension of the null space of A is the number of free variables in the equation AX equals 0. And the dimension of the column of A and row of A is the number of pivot columns in A. So I started to row reduce this, and well, the question is find the dimension of the null space of A. So we just have to find the number of free variables. For this first part, well, I started to row reduce and saw that I'm going to end up with these first 3 columns as pivot columns. So the dimension of the null space of A is going to be 1, because I'm going to have 1 free variable. So the dimension of the null space of A is 1. And what about the column and row? Well, they're both free. And I've got three pivot columns. Every pivot column gives me a pivot row. So they're going to both be 3. So the dimension of the column of A equals the dimension of the row space of A, which equals 3. And I think that's the next theorem right here. Yeah. So for any matrix, the dimension of the column of A and the dimension of the row of A are the same. It's just the number of pivot columns, the number of pivot rows we have. And the The rank of a matrix that we've talked about before, that is the dimension of its column space or its row space, either one. And the nullity is just a fancy name for the dimension of the null space. So they give it a new name. And the rank of A, where A is an m by n matrix, plus the nullity of A equals n. So it equals the number of columns. So that's what I just claimed right there. The proof is right here, but let me explain a little bit. I think this might help. Even if I have a matrix that's just one row, but I have 6 columns, then as long as one of those is a non-zero number, then I know it would span at least one dimension, and it can't span more than one dimension. But why would I need 5 other dimensions in the null space? Well, this is I really have 6 variables here. I need 6 variables, 6 coordinates or I could think about this as, I have 2 ways to think about this. I can think about it as 6 coordinates in a one-dimensional space, or I can think about it as one coordinate, one vector in a 6-dimensional space. So spanning one dimension in a 6-dimensional space, well, one dimension is just a line, but I have those other 5 dimensions. They will end up being null space dimensions. And so you can see here that, yeah, I've got 6 variables to deal with, and the span of this is only going to be one dimension, so I'm going to have 5 free variables, and all of those will contribute to the dimension on the null space. Okay, I think that's enough. Better stop.